Hi Year 12 Maths General students. This lesson is another one from Unit 3 of the Queensland Maths General syllabus, where we're using the regression model we've developed previously to make predictions. The lesson objectives are using the linear regression models we've established. We're going to use them to make predictions, and we're going to look at what interpolating and extrapolating values means. In line with that, we're also being very careful to consider the limitations of modelling scenarios, particularly when we're extrapolating, given some logical assumptions about the model. Okay, so one of the benefits of creating a model from data you're analysing is we can use it to make predictions. So for example, a doctor might want to know how much medication to give you based on your weight. And that's established from a model from studies previously done to come up with a good safe dose to give a patient. A lot of the real life models consider other factors to incorporate within the model. However, we're going to keep it very simple and we're going to just use our linear models and from that predict values within the data range we've been given and then values that might be outside of that range. If you're predicting values within the range of data you've collected already, that's called interpolation. So essentially, what you're seeing here in the highlighted blue, that's within the range of data we've collected. Any values outside of that range that you're predicting, that's known as extrapolation. So how does it work? Well, we can estimate extrapolated results from the trend line just by reading it from the graph we've established. So for example, if I was interested in approximately the height, if I had an arm span of 170, I'd go up from the arm span and then up to the trend line and then across to the height. So that corresponds with, from what I can see, roughly 170 centimeters height. However, a more accurate method is when I use the equation of the regression model we've developed. And we'll look at examples of that now. Starting off with an example where we're looking at a correlation between someone's arm span and height, we established a model equation where height equals 0.821 times the arm span plus 30.69. The first part of the question is asking us to use the model equation to predict the height of someone who had an arm span of 163 centimeters. Second part is then getting us to use the equation again to predict the arm span in centimeters of someone who has a height of 200 centimeters. So in the first one, if I have a look there, an arm span of 163 centimeters is within the data range. So you can see that I'm interpolating. For the second one, we want a height of 200 centimeters. You can see that's outside of the range. So this is where I'm using the model to extrapolate. For both parts of the question, I'm just going to write down what I know and solve for what I don't know. Like always, start with writing down your facts and your aim. So then our height is going to be 0.821 times 163 plus 30.69. So that gives us 164.51 centimeters. Moving on to part B, we now want to predict the arm span for someone that has a height of 200 centimeters. And this is where our amazing solving equation skills come back into play. So first step, we want to get rid of the plus 30.69 or minus 30.69. And then to get rid of the 0.821, we simply divide by 0.821. And that gives us an arm span of 206.22 centimeters. In our second example, we're considering the model equation we developed for that group of people where we're looking for a correlation between blood pressure and stress levels measured by the amount of cortisol in their blood. And we established the model equation. Blood pressure is 0.33 times the cortisol levels plus 53.723. From this, the question wants us to predict cortisol levels in parts per million, ppm, of someone who has a blood pressure of 78 psi, and that's interpolating. So we can see that 78 psi is within the data range. And secondly, use the model equation to predict the blood pressure for someone who has cortisol levels of 120 ppm. You can see that's way outside of the range that we've graphed there, so we're extrapolating. So again, when it comes to solving for cortisol, we just need to use our solving equation skills. So we'll minus the 53.723, and then we divide by 0.33 to end up with our cortisol levels, with 73.57 parts per million of cortisol in the blood. For part B, finding our blood pressure when cortisol is 120 parts per million, pop it into our calculators. We end up with 93.323. This brings us to consider whether there are any issues with extrapolating using the model we've developed. Realistically, you'd think that in the human body there'd be a certain limit to the amount of cortisol you produce, and there'd also be a limit on your blood pressure before things go terribly wrong and you stop functioning. So again, when we model these scenarios, we have to be super careful and recognize any limitations to the model that we might be able to think about. So we observed this previously when we looked at interpreting, in particular, the value of y-intercepts that we found. When we're extrapolating outside of the range of data, limitations to the model can also appear for particularly future values of the model. Looking at this last example, we're looking at the height of a particular species of tree monitored over time in years. And it's been modeled using the equation height in centimeters is 0.8 times the number of years gone by plus 0.3. It has a coefficient of determination value of 89%. So if you remember from the previous lesson, that means that it's got a pretty strong correlation between time and the height of the tree. First thing the question's asking us to do is to identify the explanatory and response variables. So the explanatory variable, because of the format of the equation, is our time in years, and our height is the response variable. Second part of the question wants us to interpret the slope and y-intercept in the context of the data. So if we look at the slope value, that's 0.8, and thinking about the meaning of that, that's looking at the fact that over time, the height of the tree will increase by 0.8 centimeters per 1 year that's elapsed. In terms of the y-intercept, remember the y-intercept is the beginning or initial value. So for this model, our tree started at a height of 0.3 centimeters, which if you think about is 3 millimeters tall. Okay, part C and D is where we're using our model equation to make predictions. So for C, I want to find the height of the tree after 3 years. Okay, so if I pop that into my calculator, 0.8 plus by 3 plus 0.3 gives me a height of 2.7 centimeters. And for D, okay, so if I pop that into my equation, I get a minus 0.3 and then divide by 0.8. Gives me a time of 1,878.38 years. So it's a very slow growing tree. For part E, it wants me to identify any limitations to this model, focusing on the future height of the tree. So if you think logically about living things, and we know from ecological studies that trees can live for thousands of years, but as we all know, living organisms have a finite lifespan, so we die at some stage. So an obvious limitation to this model is it doesn't consider the fact that at some point in time, things will stop growing. I guess the other consideration for most models is that there's always limits to the values you can find because of the scenario you're representing by the model. So finally, just a reminder again, when we're modeling scenarios, we can use the models we develop to help predict values. However, we always need to keep in the back of our minds that there's limitations to the model. So whenever you've developed a model, always consider what's good or bad about it. And you need to ask yourself the following questions when you're analysing the strengths and limitations. So was the data used to construct the model reliable and accurate? Was there sufficient amount of data to analyse? How accurately does the model aid in making predictions? How effective was the model in painting a picture of the relationship between my explanatory and response variables? Are there any values that just don't make sense? What aspects could be relevant when constructing the model that were or weren't considered? Alright, so I hope that helps your understanding with interpolating and extrapolating, and always being careful of the limitations of the models that you create. Thanks, Year 12s.